All right, so let's now do some examples. So since the derivative for e to the x and generally the entire family of exponential function, the rule for taking derivative is so simple, and so trust me, there will be no instructors out there giving the kind of example that hey, here's e to the x and find the derivative of e to the x. So my point is we're going to need, in our example, even though the first example, but we're going to need to do a little bit more creative work than just find the derivative of straight old e to the x or find the derivative of straight old 5 to the x, something like that. Okay, and so now let me bring everyone into example 1. And just like any other finding derivative problem, I'll just start out with a simple instruction: find f prime, the general derivative, or in Leibniz symbol dy dx for the derivative of our function. And so at this point, since we've learned the rules specifically for the exponential function family, but I have to mention those basic rules we have learned, the sum rules and difference rule, constant coefficient, all those basic rules, plus the product rule, the quotient rule, and the chain rule. Those are what I regard as the universal rules. Those rules will exist in any of these problems here, and that's what my aim here. We are going to be doing a nice mix, a nice combination of specifically rules that handle the derivative of exponential function and combined with those basic rules, with those universal rules we have learned earlier before this lecture. Okay, and so here, right here in our example 1, part A, how about I'm going to create a problem. Let's say y equals e to the x, okay, and in product with x squared plus 4x plus 1, or something like that. All right. So what I have here is an e to the x, and that e to the x is being in product as a product, and so multiply with x squared plus 4x plus 1. And so now, to find the derivative of this function right here, then what makes sense here is that we need to use the product rule. And so product rule say, so in my first step in taking the derivative, product rule say I need to find the derivative of my e to the x, and leaving x squared the other part, x squared plus 4x plus 1, the other part of the other factor in my product, leaving it the same. And now product rule says we're going to need to add. Now I'm going to leave e to the x the same, being the first part of our factor of our product there. But now I'm going to multiply with the derivative of all that x squared plus 4x plus 1. Okay, and so in this way right here, then the final answer will become quite straightforward. The derivative of e to the x is e to the x. So now we have e to the x being repeated here, multiplied with x squared plus 4x plus 1. And that's half of the work for our product rule. And the other half of our product rule, now I'm going to add with e to the x, but multiply with. So now this derivative here is just simply, we're just going to simply apply our power rules together with all this, the sum rule and difference rule that we've learned. So, or in other words, taking the derivatives here term by term. So we're looking at 2x plus 4. Okay, and that concludes our final derivative. So you can also have your choice, and so that's why at this point here I leave it for viewers to make sure you know what your instructor is asking for. When I teach my class, I have different requirements for my students. But so some instructor may require the students to combine these, because since due to the fact that we have a common factor here. So some instructor may require their students to combine these two terms as one term, so e to the x as one common factor, and these two are being combined together in one parentheses. So we're looking at x squared plus 6x plus 5. And that's another way of writing our final answer. Okay, but it's all in this video lecture here that I'm showing two different ways, but and normally the way how I see it is right here is already where you are done with taking the derivative. But do watch out in case your instructor is looking for the further simplification of your final answer. But that's how we're done part A. So quite simple, and we see what we saw here was a nice combination of the product rule and combined with those earlier rules we have learned, the power rules will be in here, and the rule for our exponential function. Okay, and so let's look at part B. And now I'm going to use my other board for part B. So how about in example 1? Once again, let's find the derivative for any of the given function here. So how about our function here is y is equal to e to the x over e to the x plus 1. Okay, so what we have here now is a quotient. It's e to the x involved, is exponential function being involved all over. And so, but mainly what caught my attention here is a quotient. So now getting into the derivative, taking the derivative of the entire quotient here, because e to the x is only one small part inside of the entire quotient here. And so in that way, I have to first apply my quotient rule. So the quotient rule says I'm going to need to find the derivative. Okay, and now allow me to use a short notation. So the derivative of e to the x, I'm going to multiply with e to the x plus 1, the denominator without derivative. And the quotient rule says further that we're going to subtract. I'm going to keep e to the x the same, no prime, and I'm going to take the derivative of e to the x plus 1, the denominator. But then there's another element. We need to divide by e to the x plus 1, the the denominator square. Okay, and so now we really are ready for finding the derivative. So e to the x, taking the derivative, is e to the x. So e to the x times e to the x plus 1. In my first term there, has become thus. And then next we're going to subtract, and then e to the x here is here, and all that, the derivative, these are two terms, but taking the derivative term by term, the first term becomes e to the x, and the second term becomes a 0. So it's just e to the x times e to the x. And then we are dividing by e to the x plus 1 all square. Okay, and then at this point right here, at this point technically we are done finding the derivative. Okay, but then in case if your instructor is asking you to further simplify the final expression to a final expression, then we can take our, you see, common factor is here, e to the x, and so I can factor out the e to the x, and here we're looking at e to the x plus 1 and minus 1, and then all over e to the x plus 1 all square. And that's not quite final yet, because we can cancel out the two opposite terms here. I mean, actually I made a little error here. It's supposedly minus e to the x here. So these are the two opposite terms. Okay, and so canceling out the e to the x being the opposite terms, okay, then my final expression for this can be, I'm going to need a moment to erase my other board. All right, so back into my other board now. Then we can come to e to the x all over e to the x plus 1 all square. So this is the simplified version of our final derivative, which again, I may not require my students, but some other instructor may. So it's all about viewers that for viewers it's all about that after you watch from here, but you've learned the generality of how to get it done. But once again, you still need to watch out for different requirements from each different instructor that you are with. Okay, all right, so let's now try another problem. So I'm going to call that part C of our example. And so now part C of our example, we can have about f of x here be a 2 to the x, okay, and divided by the x squared plus 4. Okay, so our function here, the entire function has exponential involved and some polynomial, and it's in the end it's an overall it's a quotient. All right, so finding the derivative, f prime is going to be, and here we can just apply all of the rules we have learned. We don't need to stay with the limit definitions. So quotient rule, because we have a quotient here. So quotient rule says I need to find the derivative of the numerator and multiply with the denominator, keeping it the same. And I am going to subtract further. Now I'm going to keep the numerator the same and find the derivative of x squared plus 4 from the denominator. And I'm going to divide by the square of our denominator. Okay, so x squared plus 4 came out from our original denominator. So now we're going to put that as a square in our denominator of the derivative. All right, so now in the next step right here, it's just a matter of getting these each of these derivatives taken care of. So 2 to the x gives me the derivative 2 to the x, but times with an additional natural log of 2. It's a value, it's a constant coefficient. And then times x squared plus 4. Okay, and the next term, 2 to the x, is without prime, so it just subtract 2 to the x. And I'm going to multiply now this derivative here, term by term, power rules kicking in again and giving me 2x. Okay, and so now, and we're dividing all that here by x squared plus 4 squared. Okay, and so this is, as far as getting the derivative work done, we are quite finished with that. Okay, but then in case that your instructor is looking for your simplified answer, then the next thing we can do, we can, okay, there was a common factor 2 to the x here. Let me quickly bring it back here so everyone can see. But there's a common factor 2 to the x in each term like that. Okay, and so now, but notice the natural log of 2 here is just one particular factor, so don't bring the 2 out because it's a natural log of 2. It's not ln times 2. Okay, and so now I can factor out 2 to the x, and everything in my parentheses here becomes x squared natural log of 2 plus 4 natural log of 2 minus 2x. And that's about all we can do. And we're dividing that here by x squared plus 4 all squared. But really this is about the best we can do. We can't really cancel anything. And the only thing we did was to factor out that common factor 2 to the x. And that's about all there is. Okay. And let's now look at another problem in our example 1 here. So problem D of our example 1. So we can have, how about y as a function tan to the x times sine of x. Okay. So we're looking at an exponential function being in product with a trig function. Okay, so now again, as I said earlier, we have an exponential function being in product with a trig function, but mainly what I try to point out here is we have a product between two functions. And so now when we take the derivative here, then we need to apply the product rule again. So the product rule says I am going to find the derivative for my tan to the x and multiply with the other factor without prime, and I am going to add So now I'm going to leave 10 to the x the same and take the derivative of sine to the x. Okay, and so now at this point, it's just a matter of getting each of these derivatives completely done. So 10 to the x, taking the derivative gives me 10 to the x, as we have learned from the general a to the x derivative. So 10 to the x is, when you take the derivative, it's repeating the 10 to the x and multiply with natural log of 10. Okay, according to the rule we just learned within this lecture over here. And then times sine of x. And then we're going to need to add. Now there's 10 to the x, and I am going to multiply now. Recall for yourself from earlier lecture, sine of x, taking the derivative of sine of x, of trig function, is going to give me cosine of x. Okay, all right, and so now as far as getting the derivative done, we are done getting the derivative. But again, in case your instructor is looking for a simplified answer, really there isn't much to simplify other than just factor out that common factor 10 to the x here. So we can write it out as 10 to the x and then multiply with natural log of 10 times sine of x plus cosine of x. And that's the final simplified answer, the simplified final answer for our particular problem D in example 1 right here. All right, and let's now look at example 2, where I'm still going to just do more examples where we are finding the derivative. But I want to bring in those problems where we can apply the chain rule. So let's look at example 2 right here. Okay, and so back in the lecture where I was teaching specifically about the chain rule, and I did say somewhere in that lecture that once you've learned the chain rule, really the chain rule exists everywhere in any of your problems. I mean, the earlier problems in our example 1 here were quite simple, so we didn't have to require to bring chain rule in, but you always gonna have to watch for chain rule that can be applied anywhere. Chain rule is quite universal out there. And so now let's look at something like this. How about our f of x here is instead of e to the x, that's simple. Nope, we're not going to do e to the x, that's simple. We're going to do e to the, so instead of x, it's going to be how about x squared plus 1. Okay. And so now this is where things are starting to become a little challenging in terms of seeing the inside and the outside part here. But see, this is what my advice for anyone. So this is clearly an exponential function. But see, instead of being the ordinary e to the x, okay, just think about in place of that x, that ordinary x, now we're substituting that. So in place or inside of that ordinary x, there's a whole x squared plus 1. So my advice here is generally anytime when you're looking at an exponential and your exponential components here, your exponents is just anything other than the simple ordinary x. That's, you can take all that. It's just, and back in the lecture when I was saying about chain rule, there is no such thing as a right or wrong. But what I'm pointing out here is a good advice, is an advice for you to find the best substitution, find the best inside function for your work. Okay, so here the best part to recognize, the best expression to be recognized as the inside is here, the x squared plus 1, because it looks like it's inside of that ordinary x in your e to the x. And so in that way, the outer function. So now once again, I'm going to have to pretty much reminding everyone about the way how we recognize. So inside function, the inside expression can be just regarded as this. I can go with just think about there's the x squared plus 1. That's the inside. Okay? And then the outside, once you've got the inside, think about we substitute that away. Then the outside is just the e to the x, some e to the x like that. Okay, because here we can let that be some capital X, and that's why in my outside it's e to the capital X right here. Okay, all right. And so this is my lowercase x, this is a capital letter X representing it's a different variable now, and I recognize the entire x squared plus 1 to be my inside function. And then I assign all that expression to the capital X variable. And so now once we assign and made that substitution, then the entire problem became e to the capital X. So now it looks pretty ordinary. That's the outside, it's just the ordinary e to the x function. All right. So now at this point, hopefully when you're arriving at this video lesson right here, then you are at certain fluency with the chain rule over here. So now when we actually, and that is only assisting you to recognize your inside and outside. You don't even have to do this too oftenly when you're completely on your own right here, unless your instructor is required it. Okay, so now here to get to your dy dx, the chain rule says we take the derivative of the outside. Take the derivative of the outside. It's just e to the x. But now, see, the derivative of the outside, the chain rule indeed said take the derivative of the outside, but keep the inside the same. So inside of that capital X that I just now erased, it's the entire x squared plus 1 is being there. So this is the derivative of the outside. But now chain rule says further, we need to multiply with the derivative of the inside. This inside function is here. So it's going to be simply 2x. So now we are at our, and it's quite simplified already. So our final dy dx is, and normally when it's a problem mixed between one single term of exponential function and another one single term polynomial like this, I tend to bring the polynomial in front. It's a convention that's been going on around there with the worldwide. So 2 to the x times e to the x squared plus 1, and it saves us from writing too much parentheses. But that's how we're done with our derivative. Okay. All right, so now in part B of our example, I am going to erase to make some more space in my other board. And so now we can look at, so something like this, I can, even though it's a part of our example, but now I can create a little bit of an FYT, a problem for viewers to try on your own right here. So how about an FYT? I learned this style from one of my favorite professors back then when I was in graduate school right here. But that's for your trying, for your own trying. And I believe I've done this in some of my earlier lectures right here. But so now how about y equals e to the 5x. Okay, so go ahead and pause the video and get yourself to work on that, and then when you're back, I'm only gonna write down the final answer. Okay, so because the problem here is quite simple. All right, so hopefully you're back now with your own answer. Let's compare answer here. The dy dx for this problem simply says I recognize there's an outside function e to the x, but inside is the 5x. Take that advice I've had earlier in part A. The final answer now is simply e to the 5x and having a coefficient 5 in front. That's the answer we've had right there. Okay, and so how about another FYT right here? Another FYT. So even functions, so question C, but another FYT. What about y equals e to the minus x? Think about using a chain rule here. See, my advice from earlier, anytime your exponential function, when you're looking at the exponents part here, the exponent is being more than just the ordinary x, then there we're going to start taking all that a little bit out of ordinary, the exponent there being your inside expression. Okay, so there's my advice, taking that as the inside expression. So go ahead and pause the video, have your own work, and let's find out if we agree. All right, So now hopefully you're back and had your own answer. My dy dx for this problem, chain rule says I'm going to take the derivative of the outside, which is just e to the minus x. And now I'm going to multiply with the negative of the derivative negative of negative x. So it's just that. That's my final answer. All right. So that's our problem in part C, and B and C were intended for viewers to try on your own first and to see if you agree with my work. So now let's look at part D right here, where we can, now I can lead the way. So what about another problem? How about f of x equals, how about sine of e to the x? Okay, and we're starting to have a chain rule to be applied all over. So here, what I've seen here, I can recognize, and again, what I do here is just my way, and it seems like the one that works best for me so far. But like I said, back in my lecture on chain rules, when you're applying chain rules, when you're about to recognize your inside function, then eventually getting to your outside function, there are no such thing as getting the wrong inside or the right inside. Any expression can be regarded as the inside expression, but will it be the best working one? Okay, so and it's being the best, it's out of judgment. It's not for me to judge. So far the one I choose right here, in my own experience, it works the best for me. But maybe viewers out there, you might find even a better way to find your inside right there that even works faster. That's a huge plus for you, because it's a sign that you learn good. Okay, so inside here I would recommend e to the x. It's a recommendation. Okay, and we can regard to all that as a big variable u. Okay, and then so now that means our outside function simply remains sine of u. Okay, so the outside function is the sine of something. That something here is the big variable u. Okay, so that's just a quick explanation about the anatomy of your function, where you're seeing the inside and the outside. But now let's get to work. Chain rule now says, taking the derivative here, I should use f prime symbol. So f prime of x. Chain rule says take the derivative of the outside. So that's the derivative of the outside, but the outside is sine function. So derivative here is going to be cosine. But now I am going to keep the inside function here entirely the same. So cosine of e to the x. And instead of writing u, I'm writing its actual meaning. So u here represents e to the x. So I'm going to write e to the x there. And now chain rule says we're going to have to additionally multiply with the derivative of the inside. But the derivative of the inside is just e to the x. So our final answer, cosine of e to the x times e to the x. That's our final answer, f prime of x right here. Okay, or we can write it as f prime of x. That's one way of writing it. Usually I would bring the e to the x in front. So e to the x times cosine of e to the x. All right, and that's how we're done with the problem in part D of our example. All right, so let's now do another tangent line problem. Tangent line problem is the kind of problem where I promise to any one of my calculus students, anytime throughout the quarter, throughout the learning time, I have to keep scatterly hitting back with any of my students a tangent line problem. So we have done quite often we've been doing the tangent line problem throughout the scattered lectures in the past. And so here it is, I'm going to do another tangent line problem. the intention here is to apply this skill we've learned primarily on our exponential functions. So here, what about, okay, so example 3 right here. Let's find the equation of the tangent line to this function f of x equals e to the x. Okay, but now at x equals 0. And so now when we get to this, once again we have done tangent line quite a few times throughout our time learning together. So and viewers who've been following my video, hopefully at this point watching this video, you already set for yourself into a good routine of which major steps needs to be done in order to find the equation of any tangent line. So here's our curve. E to the x is going to have a curve, and then we have a given x value. We want to find the tangent line to that function at this given x value. So first thing of tangent line, we need to find the slope. And so now but before we finding the slope, we have to find our derivative of the function. So the derivative of our function here is going to be taking the derivative of e to the x. And now that simple rule kicks in right here, e to the x. It's the derivative of e to the x. And so in that way, now that means my slope of the tangent line, see, once again the subscript t right here is indicating that the slope of the special line is a tangent line. So tangent line, slope of the tangent line is our derivative at x equals 0. The given value 0 specifically given here is being substituted in our derivative, and that gives me e to the 0. And so e to the 0 according to algebra equals 1. Okay, so we found our slope here of the tangent line is 1. That means our equation now, the equation of the tangent line is now halfway completed. It's 1x, where I don't have to write 1, so it's just x plus b. Okay, and so now the next step I need, let's find the y-intercept right here. But so now in this problem, we are only given the x coordinates of the tangent point, not the complete tangent point. So we have to find the tangent point. So the tangent point is the only thing missing, the only part missing about the tangent point is that we don't have the y value. So let's find that y value of the tangent point. So the y value of the tangent point, when x equals 0 of the tangent point, the y value here is simply the function e to the x, but substituting in 0. Okay, because our function is e to the x. So we're substituting in, I should have written one more little steps to make it clear for everyone to view and understand. But the y value here is simply the function, not the derivative, the function value at 0. Okay, and so in that way, it's going to be e to the 0, and now it's going to give me 1. Okay, so this is my tangent point, the y value of my tangent point. But now what's useful about this? Now once we have the tangent point in complete pair of values right here, I'm going to move on to my next board, erase out some space right here, and then we're going to complete our equation. All right, so now with our tangent point now found to be at, so the tangent point now is at 0, 1. So that means our equation y equals x plus b, I am going to use this pair of values, 0 substituted for x, 1 substituted for y. And so now I'm looking at 1 equals 0 plus b. Okay, and that's now obvious to see that b must equal 1. So now we are ready for making our final conclusion regarding the tangent line's equation. Our tangent line equation is y equals x plus 1. And that's our tangent line, the equation of our tangent line. On this curve, the curve of e to the x, f of x equals e to the x at specifically x equals 0. All right, so in that way, let me quickly show the graphs of the function, and as well as the tangent line, so everyone can be convinced about what you are doing. All right, so give me one more little bit moment here to prepare my grid. All right, so here we go. Here's our graphing space right here for our empty graphing space. And now I'm going to go ahead and graph my e to the x. So e to the x function. And let me turn that into red color. So in red ink, this is our famous e to the x function. So it's that going one way. And so the tangent point and e to the x is going one way from the left to the right, keep increasing, and it's increasing more rapidly. And then you should have seen this back in your pre-calculus class, that any exponential function has a similar graph structure, and they're all intersecting the y-axis as a value right here. And so e to the x intersect our y value at 0, 1. So that point right there is our y-intercept. So the graph here intersects the y-axis. I apologize if I accidentally said the graph intersects the y value, but I meant the graph intersects the y axis at 0, 1 right here. So this is the y-intercept of our graph. But then, so at the point 0, this is also our tangent point. All right, so let me now put that in black ink there. So that's our tangent point. And now our equation y equals x plus 1. Okay, and this time, and let me adjust the color to green color. All right, so in green, this is our tangent line right here. So at x, at the tangent point 0, 1, which our math work gave us right there. And now we're looking at that tangent line in green being slope 1 and going through the y-intercept. And of course, the y-intercept here is the same point where that tangent point is at.